Dhanamajuri University ki makhadaliba DM Community College ki media studio ni akhoi COVID-19 lockdown ki manungsida akhoi lisangsina chathajarakpa series of online video lectures which are uploaded and shared with the students for supplement of their maintaining their academic calendar during the COVID-19 lockdown si manungsida moigi academic akhoi calendar si de sukhara supplement oina akhoina video lecture sing upload tawjabani ngasigi class asi mathematics ki ni MSc fourth sem gi mathematics ki class lobi gedobani aduga ngasi class lobi gedoba sina DM College of Science Dhanamajuri University ki DM College of Science ki mathematics department ki associate professor ni Dr. M Bina Devi lobisi.
A very good morning to all the students of MSc fourth semester. Today we are going to do a topic on Calculus of Variation, Unit 2 of Mechanics. I'm picking up the topic Physical Significance of Hamiltonian. Before going to the main topic, I will first like to introduce some concepts. Let me begin with the Hamiltonian variables. We know that in the Hamiltonian mechanics, the basic variables that characterizes the state of a system are the generalized coordinates Qj, the generalized momentum Pj and time t, where we know that Pj is equal to del L by del Qj, j ranging from 1 to up to n. The variables Qj, Pj, T are called the Hamiltonian variables. After this, we define a function. Say a function h. A function h defined by the expression h is equal to summation j ranging from 1 to n Qj dot Pj minus L, where L is the Lagrangian of the dynamical system which are expressed in terms of Qj, Pj, T, where Pj is equal to del L by del qj dot. Now S is equal to z ranging from 1 to n qj dot pj minus l. Let us call this equation number 1. When the Hamiltonian H is explicitly independent from time t, then we have S reduces to a function of only the generalized coordinate qj and the generalized momentum pj. So we write S is a function of qj and pj only. dH by dt becomes, if we differentiate, it becomes summation of j ranging from 1 to n. Now it is only a function of qj and pj, therefore it becomes del S by del qj into qj dot plus summation of j ranging from 1 to n del S by del pj into pj dot. So again we call this equation as equation number 2. You must have heard the Hamilton's equation of motion. At this juncture we shall use the Hamilton's equation of motion by Hamilton's equations of motion. We have del S by del qj is equal to minus pj and del H by del pj is equal to qj. I am sure you must be aware of all these equations from mechanics. So if I substitute the value of this del S by del qj here, it becomes minus pj, and again same thing here, del S by del pj. If I use this equation, it can be substituted by qj. Therefore the equation number 2 reduces to, therefore equation 2 reduces to, the left hand side remains the same, dH by dt is equal to, as I said earlier, it becomes, the first summation will becomes, by writing dH by dqj as minus pj, it becomes minus pj, this is pj dot and this is qj dot. So it becomes minus pj dot, then we have qj dot here. Then for the second summation again, j ranging from 1 to n, instead of del S by del pj, by using Hamilton's equation of motion, we write qj dot and then we have pj dot. Here the first summation and the second summation gets cancelled, therefore the value of ds by dt is equal to 0. When ds by dt is equal to 0, it is very simple. We know that ice is a constant. right? S is a constant now. But S is equal to summation Qj dot Pj minus L, and this is equal to summation of this summation ranging from j ranging from 1 to n, and again here j ranging from 1 to n, Qj dot into, here we use the value of Pj, that is equal to del L by del Qj dot minus L. For a velocity independent potential field, we know that H is equal to summation j ranging from 1 to n Qj dot, instead of this L, del L we can substitute by del T divided by del Qj dot minus, instead of L we can write T minus V, where T is the kinetic energy and V is the potential energy. Now, for a scleronormous dynamical system, the kinetic energy T is a homogeneous quadratic function of the generalized velocities. Therefore, we have from the last equation H is equal to twice T minus V. This is further equal to, when we open this bracket, this become positive, this become negative, so twice T minus T is T plus V, and we know that T plus V is nothing. This is the sum of the kinetic energy and the potential energy, which will be equal to the total energy system, the total energy of the system, total energy of the system. So from here we can conclude that for a scleronormic dynamical system, when a velocity independent potential field, as if a system is moving, then it obeys the principle of conservation of energy. So let me write it down. This is the last part of this physical significance of Hamiltonian. For a scleronormous dynamical system, when a velocity independent potential field, it obeys the principle of conservation of energy. That's all for today, my dear students. I hope you understand, and if you have any difficulty, you can call me and I'll explain to you. Thank you very much.